Assalamu alaikum wa rahmatullah everybody, and welcome to session number 5 of the training titled OFDM as a key transmission technology for many different applications and use cases. So in today's lecture we will be talking about MIMO OFDM, and hopefully if time permits we will talk also about the simulation and the hardware implementation of real practical systems, how to design a practical wireless system, transmitter and receiver from A to Z. But before we get started, let's give you an overview about the previous topics we have discussed so far. In the previous lecture we discussed about mainly OFDM design, the parameters that we need to take care of while we are designing the OFDM system, the key design parameters in terms of number of subcarrier, guard time, symbol duration, subcarrier spacing, modulation, and forward error correction. Then the requirements of the system, the requirements of the application and the environment we have, and then the relationship between these parameters and the key performance metrics for any system, and then the effect of the channel on that and how to take into consideration the channel parameters as well. And then we gave an overview comparison between the three main modulation schemes that were used in the previous generations and why OFDM was chosen as the dominant and successor waveform to be used in 4G and 5G. Then we moved to the 5G systems and we discussed how OFDM has been manipulated in order to meet the requirements of new emerging application like ultra reliable low latency massive machine type communication and enhanced mobile broadband. So we discussed exactly the key differences between the OFDM that was implemented in LTE and the OFDM that we are going to implement in 5G. And the key parameter we have seen altogether that the key parameter responsible for modifying and adjusting the OFDM in such a way that it can meet the requirements of different applications is the subcarrier spacing. We said that in 5G we have too many different use cases, too many different applications and services, and we cannot find only one single design that can meet the requirements of all these applications. So to overcome this problem, we played with the subcarrier and we showed you how the subcarrier width can change the symbol duration, can change the power of the packet or symbol in time, or the power of the subcarrier in frequency, and how these symbol parameters are basically the fundamental components responsible for controlling the latency and reliability and adjacent interference and even providing high data rate. And we gave example of multiplexing numerologies with each other and some other details and the frame structure of OFDM. And also we mentioned that OFDM is considered as the downlink modulation scheme in 5G, while in the uplink we can use either CP OFDM or DFT spread OFDM. And there are also some talks from several companies that they want to use some other waveforms in order to enhance the out-of-band emission. But we mentioned one important point, that DFT spread OFDM, we said that there is a very important feature in DFT spread OFDM, that it reduces the peak to average power ratio, and that's why we need to use it in the uplink, because the user device, the smartphone, the power amplifier capabilities is not that high at the user device. That's why we cannot use always in all the cases CP OFDM. But we also said that CP OFDM is very friendly with MIMO, and we will now discuss why it's very friendly with MIMO. And that's why if you want as a user to send more than one stream, let's say 2, 3, 4 streams in a MIMO transmission case, then it would be better to use CP OFDM and the uplink. So now we'll talk about MIMO OFDM and then go to some of the guidelines related to simulation and practical implementation. MIMO OFDM. Let's first, before we go to MIMO OFDM, let's go and talk about MIMO as a side component, on its own. What's MIMO? So MIMO, multiple input, multiple output. The key point here that instead of sending your data in one stream, you are sending your data by utilizing multiple streams. And the three main categories of MIMO that we see usually in the literature and being implemented in the practice are spatial multiplexing and transmit diversity and beamforming and spatial modulation. We have four main categories for MIMO in the literature and in the practical system. So let's before we talk, let's discuss the beamforming thing. So let's move here back a little bit and discuss the beamforming simply. What's beamforming? So you have here a transmitter, and you have a receiver, and you want to beamform your signal. Why do you want to beamform your signal, and how MIMO or having multiple antennas can help in that? So originally you transmit your signal from one antenna and it reaches one antenna. So if you are transmitting using omnidirectional, so the signal can go in all the direction and it can reach, let's say, up to this limit. But what if you want your signal to reach farther distances? Let's say this is 1 kilometer and you want your signal to reach 5 kilometers. What's the option what are the possible options? Either you increase the power or you narrow the beam so that it can reach longer ranges. So here where beamforming comes into the picture and fits to this case. So suppose you have three antennas, the new case, and you have one symbol S1. So this S1, instead of sending it from one antenna, you send it to three antennas, and you adjust the phases. The symbol is the same, but you multiply it with certain phase, E to theta 1, E to J theta 2, E, J theta 3. This theta 1, theta 2, theta 3 are angles, phases, that you use them, you adjust their values in such a way that the beam is focused in the direction of the receiver. So all these antennas together, when you adjust the phases of them, they will be focused towards the user, Rx. And by changing the phases, you can change the direction of the beam in such a way that it can follow the user from one step to another. Now, how do you design these phases? Assume you are in line of sight environment. If you are in line of sight environment, we have two cases: line of sight environment and non-line of sight environment. Line of sight environment, I mean by that the transmitter and receiver are seeing each other direct, point to the point. So in this case, how do you beamform your signal? You beamform your signal according to the angle of arrival with respect to the receiver. So you calculate the angle between the angle that this antenna makes with respect to the position of the user at the receiver. And suppose you found it to be theta 1. So you take this into account, you kind of compensate this effect while you are designing it. You compensate for the effect of theta in such a way that the signal, the beamform that you generate, it's focused totally on the position of the user. This is line of sight. So in line of sight, the theta is coming from the geometry, the location of the antenna at the transmitter and the antenna of the receiver at the receiving side. So the thetas, you get them from the geometry, and while you multiply these thetas with the symbols we call them sometimes phase shifter before the antennas. You adjust the phases in such a way that the beam is focused only at the location of the user. Now, what about the non-line of sight case? Non-line of sight case. you have one antenna, you have multiple antennas, sorry, and you have one receiver, let's say so many antennas. Where is the issue here? Here there are buildings here, there are trees, there are cars. The transmitter cannot see the receiver. In this case, we call them, they are in non-line of sight environment. So the transmitter sends the signal gets reflected of this, of that object until it reaches the receiver. And the same here. And you have only one symbol you are transmitting from all the antennas so that you can beamform it. So what's theta in this case? How do you design your theta, the phase shifter of each antenna, in such a way that the signal is focused at the location of the user? Simply, you just measure the channel H1 between the receiver and the first antenna, H2, the channel between the receiver and second antenna, H3, the channel between the receiver and third antenna, and so on and so forth until you finish all the antennas. And what you do now, this channel is basically the fading channel. It has amplitude and phase, H1 and phase for H1. So you take the phase and you consider it the phase that I should adjust or compensate for so that my signal is concentrated on the location of the user exactly. So what do you do here? Here you take the phase of the channel and multiply by its negative, minus e to minus j theta 1. And then next antenna, e to minus j theta 2. You get theta 2 from H2, theta 3 from H3, and you kind of pre-equalizing, removing the effect of the phases caused by the channel in the reception. So this is what beamforming is and how it works and its importance. Its importance that it can focus the energy on one location around the user only, or extend the coverage in case of line of sight. Instead of reaching only 1 kilometer, with beamforming you can reach more, 5, 6, 7, by just adjusting the beams. And because the physics theory, what it says, this is your energy. Yes, let's say your energy is this. This is the amount of energy you have. If you squeeze your energy and make it only within this duration, within this side, within this space, so what will happen? Your energy will bob up from the front of the waveform. So when it pops up from the front, which means that you are reaching farther ranges. You are reaching longer distances, and here your beam becomes narrower, which means that you cannot cover too many users around you in all the directions simultaneously. Wi-Fi is usually using this omnidirection, all the direction, but in the future 5G and massive MIMO and millimeter wave, we always need to use beamforming in order to reach farther distances and compensate for the loss due to the channel, due to the propagation. Now this is beamforming, simple. Now let's move to the next type of MIMO. What's the next type of MIMO? Spatial multiplexing. What's spatial multiplexing? You get you have your stream of data, yes? You split them, you spatial multiplex them, split them into multiple streams. You take S1 and put it to the first antenna. You take S2 and put it to the second antenna. You take S3 and put it on the third antenna, if there is a third antenna, and so on and so forth. What's the good thing about this? We understood before few minutes the importance of beamforming and how beamforming can help us improve the coverage, reduce the interference by narrowing the beam, and also improve the overall reception quality. But what about spatial multiplexing? Here I'm not multiplying by phases or compensating for the effect of the channel or so on and so forth. What's the key advantage that I get from spatial multiplexing? The key advantage is to increase your data rate by sending multiple symbols in parallel, where you feed each antenna with a stream of symbols. Now, you tell me this is great. I mean, in case of MIMO, I'm sending only one stream. Here, I'm sending multiple streams simultaneously to the receiver. But why didn't we use this technique long time ago? Why didn't we? Spatial multiplexing started to appear in the literature around 1996, 1990, and 2000. In that duration, they started thinking about spatial multiplexing and that it can be used to improve the data rates of communication systems. And accordingly, in 2006, 2005, they started using it in 3G and Wi-Fi, and after that in MIMO, in LTE. So it helps dramatically, it helps increasing the spectral efficiency and accordingly the data rate and the speed of the internet in a very significant way. And the point is that MIMO spatial multiplexing is a technique that's uniquely dependent on the characteristics of the channel. So for this technique to work properly and for you to be able to separate the transmitted symbols properly, you need to have a multipath, rich scattering multipath channel here between the transmitter and receiver. The transmitter and receiver should have between them rich multipath scattering channel, so that the receiver can use these differences in the channel in order to distinguish between different transmitted symbols, and then accordingly you are able to separate between them. Because if you transmit multiple symbols in parallel but you are not able to separate between them, then what's the point? You are causing interference to yourself, and therefore you won't be able to benefit anymore from this transmission. You won't be able to benefit from transmitting multiple symbols simultaneously because you are not able to separate them and put them one back to other in such a way that the receiver can understand them and then decode them properly and transfer them to upper layer and then hopefully see your video or your image or your text. So this is the key. Who invented spatial multiplexing? Who's the guy who was behind this? And the mastermind of this spatial multiplexing and introducing it to the literature. So the guy is Indian professor who was working in India in the Navy for like long period of time, 20 years, I don't know exactly how much. But then he moved to USA, to Stanford University, and he came with his students while he was working in the lab and trying to separate the multipath, the signals being received from multiple directions. He noticed something while he was making some tests in the wireless environment around the university, practical tests using hardware equipments, that if the channel is really rich scattering, then you can use the differences in the channel as footprints, as prints, so that as fingerprints, so that you can distinguish and separate them properly. That was the problem. The problem was not to transmit multiple symbols from different antenna. The problem in how to separate them. And you can only separate them if you have a rich multipath scattering channel. Now the question is that, so you mean that MIMO spatial multiplexing cannot work in cases where we don't have multipath? MIMO spatial multiplexing cannot work in environments where you don't have rich scattering multipath. Yes, that's right. It cannot work if you don't have rich scattering multipath. It requires, for this to work, requires multipath. Multipath is important. Now, what does this mean? This means that if you have an additive white Gaussian noise channel, does this technique work? No, it doesn't work. You cannot. Why? Because we call it in math the rank of the channel. The rank of the channel is not full. Even if you have, let's say, 3 antennas or 100 antennas at the transmitter and 100 antennas at the receiver, and you are in a line of sight environment, You cannot get this gain, the MIMO spatial multiplexing gain. MIMO spatial multiplexing requires a rich scattering channel in order to be able to separate between the multi symbols. So if you are in an environment where you have additive white Gaussian noise only, it will not function. It will not give you enhancement in the data rate based on the number of antennas you have. So typically when you have a rich scattering multipath and you have, let's say, m number of antennas and m number of receivers, then the number of multiple streams you can send simultaneously is m is equal to n. And for example, suppose the data rate from each antenna is 10 mega, and you have 100 antennas, and you are using spatial multiplexing in multipath environment. Do you know how much your data rate will be? 100 multiplied by 10. It's equal to 1000 mega, which is 1 giga. So imagine the effect of antennas multiple in increasing your data rate. It's very significant, very amazing. But unfortunately, it cannot work in additive white Gaussian noise, and for that we need to create some really novel and intelligent solution. For example, in millimeter wave communication, does this work? Very hard to make it work. It cannot even work sometimes. Why? Because the millimeter wave, you are operating at 60 gigahertz. 60 gigahertz, there is no much reflections. You cannot get some rich scattering environment at that point, at that frequency. Therefore, your channel is not full rank, which means it cannot support more than 1 or 2 streams at maximum, which makes you lose the advantage of spatial multiplexing that MIMO brings. But why do we still say that millimeter wave can work and it's good? Because it has large bandwidth. You are operating at 60 gigahertz. The bandwidth there is 1 or 2 or 3 gigahertz, so you can compensate for the loss in the spatial multiplexing by the bandwidth you have in the frequency domain. So you send the data in the frequency domain and you increase your data rate. That's why we call and we say that in millimeter wave we are still increasing the data rate significantly. So this is spatial multiplexing briefly. Last point to mention about it: if you have M transmit antenna and M receive antenna, and N and M is larger than N, what's the maximum number of data streams you can get? N. And what's the total data rate you can get if your data rate for one single antenna for one stream is, let's say, R? The total data rate is M multiplied by R. If the number of antennas at the receivers are larger than the number of antennas at the transmitter, what's the maximum number of independent data streams you can transmit? The maximum number of data streams you can transmit is also equal to M. So M is, so for this case, when M is greater than N, so the maximum number of data streams you can transmit is equal to the minimum of both. Yes, suppose you have here 10 and you have here 5 antennas at the receiver, 10 antennas at the transmitter. How many independent different streams you can transmit? 5. I can transmit only 5, because it depends. It's at the end of the day you are forming a matrix, and the rank of the matrix depend on the full rank depend on the number that has lower value. And here, for the case where you have here 5 antennas at a transmitter and 10 antennas at the receiver, what's the maximum number of independent data stream you can transmit? 5. So the rule is this: the minimum of the number of antennas at the transmitter and number of antennas at the receiver. You find the minimum. let's say if n is the minimum, then the increase in the data rate is n multiplied by the data rate for size of channel. If m is the minimum, then you multiply m by the data rate of the channel. That's the goal. That's the rule. The number of, if you don't have rich scattering multipath, you don't get any of these. You get one, only, always one. If you have additive white Gaussian noise, this single simple fact, sometimes you don't even, you read so many books, you read so many papers, and you don't get this important information that MIMO spatial multiplexing does not work in additive white Gaussian noise channel. Does not work if there is a line of sight environment. Does not work if your environment is not rich. This is very critical, because this now pushes you to think beyond that. What if I have line of sight environment? What if I want to make something similar to spatial multiplexing in line of sight environment? Can I bring something like this? Can I make this? This will make you the second inventor after the one who invented spatial multiplexing. You make very significant contribution to the work of communication if you can do this. So now let's return back to we discussed up until now, we discussed beamforming, and we discussed spatial multiplexing with normal MIMO without OFDM. Just let you know what's MIMO. Now let's go to the transmit diversity. The third category of the different uses of MIMO is transmit diversity. What do I mean by transmit diversity? Transmit diversity says that instead of sending your symbol, like in spatial multiplexing, we send different symbols, S1 and S2, different symbols from different antennas. Yes, antenna 1 and antenna 2. In transmit diversity, you send the same antenna, you send the same symbol from all the antennas, or kind of from different antennas. So here you don't send S2, you send again S1. What's the point here? And this is, now you might tell me this is similar to beamforming. We are sending the same symbol from the all antennas, but beamforming uses some pre-equalization for the phase to concentrate and the signal. This also has some similarities with beamforming, but the point here is to create multiple paths, so that if this path is in deep fade and you were not able to receive your signal correctly, you can receive it from the other path. Basically here the goal to reduce the probability of losing your symbol at the receiver, because you have multipath environment here, and fading here, all of them. Now if you only have if you only have one link, and the probability of receiving the probability of encountering an error, let's say it's 0.01. Now, if you have multiple links, let's say 10 links, what's the probability now of encountering error from all of them? 0.01 divided by all of them, 10. So it becomes 0.001. It becomes something like this. The probability becomes much lower, 0.0, the probability of receiving your data wrongly, or you are not able to decode. So having multiple antennas and creating multiple paths can help reduce your errors, and therefore improve your bit error rate by increasing the diversity. We call it diversity. Diversity means you are sending the same signal, the same symbol from different sources, whether at the antenna or at frequencies or at time. So we call it repetition. You are repeating the transmitting kind of from different sources. But why it's important? It's very important and very critical when we have multipath rich scattering channel, because rich scattering channel multipath environment is random. You don't predict it. Sometimes it's good, sometimes it's bad. What if it's very bad in this link, at least you have another link from where you transmitted the same symbol, and there is a probability that the second link experiences a good channel. And if it is good channel, there is probability that the information over this link will be received correctly. So this is transmit diversity. But now, if you only transmit your signal like this from different sources without putting them in a proper encoder, you will not get very good performance. Therefore, the researchers tried to think of how to arrange and organize the transmit symbols before I transmit them in such a way that I can get full diversity from the channel. What do I mean by this? Let's go to this figure. The researchers came up with a new transmission scheme, new encoding scheme for the MIMO system in order to improve the diversity. So spatial multiplexing improves the data rate. Here you improve the diversity. When you improve the diversity, you increase the reliability. You reduce the bit error rate. How to do that with MIMO? We have in the literature what we call Alamuti coding. Alamuti coding is named after the inventor of this coding. He was a master student when he invented this, and then opened the company, and then patented this idea and started licensing this to the industry. This technique, single technique, is still being used in LTE, in Wi-Fi, in many other systems. The Alamuti coding space-time in order to improve the reliability. So basically, without the knowledge of the channel, without knowing thetas and without estimating the phases and compensating for them, the Alamuti coding principle, Alamuti coding method says that you take two symbols and you want to transmit them and you want to exploit full diversity of the channel. Take symbol 1, S1, and put it on the first antenna. Take symbol 2 and put it in the second antenna. So symbol 2 is here. Symbol 1 is this, you put it here, and symbol 2, you put it in the second antenna. And you transmit, and what do you do? We call it the first time slot. This is time, this direction is time, and this is space. You have antenna 1, antenna 2. So in the second time slot, this is let's say T1. T1, this is the first time slot. In the second time slot, T2, you transmit the conjugate of the symbol. So this, in the first antenna, you transmit the negative conjugate of the second symbol you transmitted from antenna 2. And in the second antenna, you transmit the conjugate of the first symbol that was transmitted from the first antenna. Now you tell me what's this conjugate and this magic that you are showing us here. But I tell you, when you put them like this, conjugate, you know the conjugate is kind of negative. Converting your complex number, when you multiply by its conjugate, it converts the complex number into one value. There will be no imaginary side of your value, of your signal. So if you arrange it like this, and when you transmit it over a multipath channel and gets multiplied by H1 and H2, at the receiver side, you will get S1 and S2 separated nicely without any interference between them, and you are getting the gains of the channel in the same direction. So they are always co-phasing. They are always, we call it constructive addition, not destructive, constructive. Always you add them while they are in the same phase. Always they are aligned in the same direction. So this is what you get. You get S1 multiplied by, let's see, let's just put it with different color and explain to you what you will see at the receiver. At the receiver, you will get something like this. S1 multiplied by the magnitude of h1 square plus magnitude of h2 square at the receiver, yes? At the receiver in time slot 1. And at the receiver in time slot 2, you get something like this. h1 square plus h2 square. Now, what's the good thing? Here time slot 1, here time slot 2 means no interference between them. No interference, which means they are separated properly. And the second thing, you get them, what? You get them aligned. There is no imaginary part. They are aligned. There is no phases that removes the effect of multipath or reduces your diversity gain. So the advantage at the end of the day, you are improving your bit error rate, improving the diversity, and separating the two symbols properly without any interference between them. And this is how you get very high good data rate. Now, up until now, we discussed three cases. We discussed beamforming, spatial multiplexing, transmit diversity. What else? What else do we have? Now, let's think, what else do we have? We have another new type of MIMO transmission called the spatial modulation. You remember in communication course and digital communication course, we used to learn this concept, ASK, amplitude shift keying, where you change the amplitude of your carrier based on the incoming data bits. If zero comes, make it low. If 1 comes, make it high. And we have phase shift keying, where we change the phase based on the incoming data. If 0 comes, the phase make it 0. If 1 comes, the phase make it minus pi or pi. So your modulated waveform becomes like this. Your modulated waveform for ASK becomes like this. In case you have frequency shift keying, you have changed the frequency based on the incoming data. If you have 0, make the frequency high. If you have 1 coming, make the frequency low. If 1 comes, make the frequency very high. If 0 comes, make the frequency low. So this represents 0, this represents 1. In this new modulation scheme, spatial modulation, a new feature, which is the antenna, is used in order to send extra amount of information. So it works like this, not with the sinusoidal carrier. Now it works like this. We call it antenna shift keying. Antenna shift keying. If 0 comes, activate the first antenna. If 1 comes, activate the second antenna. So this is how it works. Based on the incoming data here you have in your stream, you activate the antennas, and once you activate a certain antenna, you send the symbol from that antenna. Okay? Once you activate a certain antenna, you send the symbol from that antenna. So this spatial modulation is relatively new compared to the previous schemes and the beamforming, of course, the beamforming. So if I ask you how many different modes MIMO can use in its transmission, we have 4 modes up until now: beamforming, spatial multiplexing, transmit diversity, which is alamoti, and spatial modulation. Of course, this is very brief description of these modes. This is just to get you started and to understand the basics of them. But I don't exaggerate that each one of these techniques, each one of them has at least, there are 10 books on them, more than thousands papers on each of these techniques, on each of these thousands papers, tens of books, so many material available online on each one of these techniques. And beamforming, even antenna guys and microwave guys, they study it, and from their domain, there are more than 10,000 papers on that, even more.
So it's very, this is the fundamentals of MIMO by its own without integrating it with OFDM. And now we will reveal the secret why MIMO likes OFDM. Why MIMO, right? Why do we always say MIMO with OFDM? What's the relationship between them? They are relatives, close relatives, and they love each other. And we want to discover the reason for this strong love between MIMO and OFDM. So the point is that LMOT coding, transmit, all these techniques, they like seeing flat fading channel. Flat fading channel is not always possible because it depends on your data rate and depends on your environment. But the beautiful thing that OFDM enables us to do is it can convert any frequency selective channel, any dispersive channel like this. This is frequency selective channel into flat fading channel over each subcarrier. You design the subcarrier spacing very small in such a way that when you come and measure the fading on it, you see a constant, always constant. Always constant. I don't see a curve over each single subcarrier. I don't see fluctuations. I don't see ups and downs in the channel. Therefore, MIMO is friendly with OFDM, or OFDM kind of make the transmission process very easy and simple for MIMO. Even if you are in a multipath, rich scattering, frequency selective, time dispersive channel. And this is nothing but LMOT. This is LMOT coding. And DK here is like, you think of it S1, S2, and this, and you are conjugating them. But I want you to focus on this. OFDM converts frequency selective channel to parallel flat channels. Which means you have only one constant, one response, one channel response, which is one complex value corresponding to each subcarrier. You don't have multi-tab filter kind of for each subcarrier. You don't have. That's why MIMO and OFDM can be integrated with each other seamlessly. And they like each other. That's why in the MIMO, in the uplink of 5G waveform design, they propose to use MIMO. Although MIMO has high peak to average power ratio, but they need to use it because it's friendly with MIMO. If the user wants to upload to the network high definition videos, like let's say real-time gaming, high-definition videos, streaming this. You cannot do this with just one single antenna. You need multiple antennas and larger bandwidth. With OFDM, you can do this. With DFT spread OFDM, you cannot do this because it's really difficult and it increases the complexity. So now we have the space that we discussed these things. Also, with OFDM, you can get antenna diversity where you transmit your. Now let's just tell you, when you put OFDM with MIMO, what happens? We discussed MIMO alone. Now when you put OFDM with MIMO, you basically just put the OFDM modulator before each antenna. OFDM modulator before each antenna. In case you are using delay diversity and you send the same OFDM symbol, the same OFDM data from several antennas, you transmit OFDM modulator from the same antenna, the output of it, and then you get another branch of it, make some delay, and transmit it from the second antenna. And that's it. This brings you diversity for it. Why do we need to make some delay here? Anybody can guess why do we need to make some delay here? Because the channel, when you transmit it from this, the channel is most probably, if you don't make delay, the channel is going to be the same. If the channel H1 and H2 are the same, you don't get diversity, because diversity is all about creating some differences, receiving different responses, so that if it is bad in the first, it's good in the second. If it is bad in the second, it's good in the first antenna or first transmission. When you create a delay, you utilize the decorrelation in the channel in time domain. So if you, and not only the space domain, but also the time. For example, if this antenna and this antenna, both of them are seeing correlated channels, their channels is not different, which means that you can make the channel different in the second antenna if you delay your retransmission by certain time, so that it can experience different channel due to decorrelation in time, in temporal domain, not in spatial domain. And this is one of the way to overcome the correlation in wireless channel, because we don't like correlation. Usually we like to have independent random channels so that we get diversity. And for the case of spatial multiplexing, for example, before transmitting your data from each antenna, you design an OFDM modulator. It takes the data from the frequency domain to the time domain, adds CB, and then feed it to the RF chain, and from RF chain to the antenna, and then to the channel. And here at the receiver, you can jointly decode them. Now, this is a structure that shows you how to implement OFDM with MIMO, block diagram. So here, what do you have here? Let's together check. So you have your data bits generator, which are coming from your application. It can be, the application can be video, message, text, whatever. And then you encode the data using forward error correction. We talked about it in the previous lecture. Then you modulate it using a certain modulation scheme. And then after that, you feed it to an encode space-time coding. Now, what's this space-time coding? Think of this like Alamuti coding. Alamuti coding, but this is different than Alamuti coding, because Alamuti coding was proposed for only the case of two antennas at the transmitter. But space-time coding is a more generic technique that can work with any number of antennas. So after you encode your data here, you take, for example, one stream, you encode it using space-time block coding, and then the output from this matrix, you take it to OFDM waveform design structure, where you have I50 modulator driving each antenna. And then you transmit over the channel. At the receiver, you have the antenna. You receive from all the antennas simultaneously. And then you have channel. Then you get the data. You estimate the channel in order to equalize the effect of the channel. And you do some decomposition in order to help designing this decoder. Now also spatial multiplexing works in the same way. You have I50 with each antenna, but here you don't have encoder here. You have kind of, sometimes you can use different encoders, or you can leave them as they are. And the detection process in the frequency domain after you take F50. So here another example where it shows you the same thing, but here general encoder. It can apply to both spatial multiplexing and the space-time block coding. And you have the I50 CB here with the antenna. You transmit, there is a feedback between the transmitter and receiver, the channel estimator, and then you transmit over the channel, and then you take the F50 after each antenna, then MIMO decoder joint for all of them, and then demodulation. So basically it's straightforward. MIMO is friendly with OFDM is very friendly with MIMO. Both, they like each other and they coexist seamlessly and peacefully. And because of the fact that MIMO likes having flat fading channel. Flat fading channel means no dispersion, no selectivity in the channel, and OFDM ensures that, enables that, and that's why we like it to be used with MIMO.
So, MIMO OFDM, in addition to time and space, OFDM system can exploit frequency diversity. If feedback channels are available, space-time frequency water boring possible, OFDM can convert delay spread diversity into space diversity, which we call diversity conversion. So, and OFDM can exist with MIMO seamlessly and nicely. So now I assume from you that now you know the basic stuff about MIMO and OFDM and the relationship between them and how they are related and the important features they are having that makes them really good friend and like each other, and always you implement them together in your systems. Now we can stop here. It has been around 1 hour talking and explaining this MIMO OFDM. We can stop here and continue after 10 or 15 minutes. I will send you the link for that. Thank you very much.